Okay, let's get started. Can everyone hear me?
Yeah.
Yes.
Good. Okay. So first off, does anyone have any questions from last time? Right. So I wanted to issue two corrections to not yesterday, Monday's lecture. The first is I said that the indigenous people of Greenland were called Eskimos. That is incorrect. I read this in a book that seemed very academic, but it was also published in the 70s. The reason for this is because in the 70s, the governments of both Greenland and Canada referred to certain portions of their indigenous populations as Eskimos. That has since changed. The proper term is Greenlandic Inuits. And part of that is because the governments were partially responsible for putting the labels in the first place. And second off, because the term became a generic term to group indigenous populations, even when they were completely unrelated. So Greenlandic Inuits is the right term. Oh, and second off, the fallacy that Odysseus committed that he used to trick Penelope, that A implies B, B therefore A, that is called affirming the consequence. Well, anyway, okay, on to today's lecture. So to start off with, I want to remind everyone where we got to last time. So we started with this model of we have apples in a basket, and we talked about numbers in this way. Numbers are introduced in this way in kindergarten when you're initially teaching children about numbers. Teachers have to get across this idea that numbers form a progression, and you can count up to any number. And then we had a definition of addition that was motivated by this. But then we said, well, if you look at properties of apples in a basket and addition in the way that we defined it then, it's clear to us that addition is commutative, that A plus B is the same as B plus A. And that's because we have this idea that if we take objects and we shuffle them around, we're not going to change the amount of objects that there are. But if we want to establish more non-obvious properties about numbers, then the fact that it's clear to us is a bit of a problem, because how do we go from what is clear to what is unclear? There are no clear rules of reasoning, no clear rules of how we can proceed from one claim to the other. And so that's why we said, well, let's try and make a bit of a more formal model of numbers. And in this more formal model of numbers, maybe we'll be able to find some other reason for why A plus B is the same as B plus A. And then to start off with that model, for us, that model is called NATS. So what is a NATS? Well, a NATS is not a number. A NAT is a model of numbers. And the rules that we got to last time were that a NAT is either so in the first case, Z, or in the second case, it is S of N, where N is the NATs. So that's where we were last time. And We also said, well, how does this definition make sense? Well, concrete examples of NATs, here are some numbers or numerals, and here are their NAT equivalents, just to see in what way it is that NATs model numbers. Well, the number Z is modeled by the NAT Z. The number 1 is modeled by the NAT S of Z, or the successor of Z. And 2 is modeled by S of Z. So S, when thought of as the successor, suggests that NATs also form a progression like numbers. And the way that you go along this progression is you take your previous NATs and you enclose it in parentheses and this S. And then we said, well, this definition looks self-referential. It looks recursive. Why is it that this definition makes sense? And on the discussion of why it makes sense is that it lets us say which strings are NATs and which strings are not NATs. So for example, if we wanted to show that, let's do this example again. Or let's do a similar example. S of S of S of S instead of Z. This is not a NAT. Now, why is it not a NAT? Can someone go over the argument that we did last time? Please.
We could try breaking it down by going from the outermost layer, where by 2 we see that it's a NAT if S parentheses SS close parentheses is a NAT. So then we look at
right. So let me write that down. Assume this is a NAT. Then, since it is not Z, it must be of the form S of N, where N is a NAT. Okay, continue. Sorry, go on.
So you mentioned that this was called analysis, in which we like tear it down. So we can go to the most inner parentheses, SS, but we see by 2, SS can only be a NAT if S by itself is a NAT, but the only thing that can be a NAT by itself is Z by rule 1. So we see that as not a NAT.
Right, perfect. So this analytic approach, analysis, we tear it down. We keep doing this. We keep asking, imagine that it's a court case. Imagine that you're interrogating a witness and the witness says, this thing, it's a NAT. And you say, really, is it a NAT? Well, if it is, then it must be either Z or S of N, where N is a NAT. And then you keep asking, well, which is it? And then if it's the second case, you do this over and over again. And eventually, either you reach the bottom and you don't find a contradiction, or you do find a contradiction. You find that one of these two rules doesn't apply, and you assume that something was a NAT, and you can't show that it's a NAT by one of these two rules. So then you know that it's not a NAT. Now, if it is a NAT and you do this procedure of breaking down and you reach the bottom, well, you fail to find a contradiction. And it's not necessarily clear that you've shown that it is a NAT. It sort of is, because then you can take this process and you can do it backwards. You can start from the last thing that you did, and then you can build it up. And then you can show that something is a NAT by building it up. So specifically what I mean by that is, can someone else tell me why S of S, by the way, good job, of S of Z is a NAT?
Well, we would start with rule 1, and that our starting point is z. And then the second rule goes, it can be Sn, where n is a nat. And since we already know that z is a nat naturally, that follows the rule. So now that becomes a nat in and of itself. And then we go to the next parentheses, S Sz. And since we know that Sz is already a nat, we know that one more S would make it also a nat. So that process continues on.
Yep. Good. Right. Right. So that shows to us that this definition, that a knot is either Z or S of a knot, makes sense, and at least that it's not hopelessly self-referential, because if we have any string, we're able to tell if it's a knot or if it's not a knot by using one of these two processes. Now, how do we know that this always works? Well, so here's the algorithm, and the argument isn't formal, the argument is intuitive, but this should intuitively convince you that you can always find the answer or find whether something is a knot or not a knot using these rules. So the argument is we're going to use the process of analysis. At every single stage in analysis, either you're at Z, in which case you're done, you haven't found a contradiction, and then you could go backwards and build it up. Or well, there are three options, or neither of the rules applies, and you can conclude that it's not a knot, something breaks, or you apply the second rule and you go inside. But when you go inside, the length of the string that you are looking at becomes shorter and shorter. And if it shortens each time, this process has to stop eventually. Now, when it stops, it can stop in one of two ways. Either it reaches rule 1 and you're happy, then you can build it up going backwards, or no rule applies and then you conclude that it's not a knot. So what this argument shows is that these two rules let us say whether any given string is a knot or not. Does anyone have any questions about that? Okay, now let's get into a bit of the details of what we really did here. There are a few important clarifications that I need to make. So the first important clarification is that I said that if n is a knot, then S of n is a knot. Now, the n that appears here is something called a metavariable. What does that mean? That means that if you look at literally the symbol n, the small character, let's say the character n, does not appear in any syntactically valid knots. Specifically, just the symbol n is not a knot. So for example, if you read this sentence as the symbol n is a knot implies that the string s of n is a knot, then the hypothesis would never be satisfied because as n is not a knot. What the sentence is that it's a production rule. Specifically, n is a variable in the English language. The language of knots, which has in it only strings like this, doesn't have variables. But if we want to describe a rule in English about how to form knots, we might want to use a variable to describe it. So what this means is that if we make any substitution for n, then we get a concrete rule. So this isn't a rule as much as it is a process for generating any type of rule. So you can think of instances of this rule as, for example, if z is a knot, then S of z is a knot. Now what I've done here is I've taken n and I've replaced it in both cases with z. So I've done this consistent replacement. This is by replacing n with z. And this situation is known as n is a metavariable. And I'll explain this name. And I've used a few words which are new, and I'll explain them as well. Now, I want to give another example of how you can substitute into this rule. You can also say, for example, if S of S is a knot, then S of S of S is a knot. And I get this rule by taking n and substituting in place of n S of S. Now, S of S is not a knot. So the hypothesis, if S of S is a knot, fails to hold. So you can't conclude that S of S is a knot. But the rule that if a conclusion which is false, then this conclusion still makes sense. It doesn't say anything meaningful because the hypothesis doesn't hold, but this idea is that you can take any string and you can substitute it for n, and then you get an assertion, a conditional assertion. If something, then something. The hypothesis, the if part, might not hold. Then you don't necessarily have the conclusion. But you can always substitute and you can always make this hypothetical statement. Now, why is it called a metavariable? The reason is that variables sometimes make sense in languages that you're discussing. So for example, in math, we frequently have variables. But sometimes we're going to discuss the language of math, and then we might have variables both in the language of math and in English. Variables in English would be these, well, what is a variable? A variable represents something. You can, if you know what that something is, you make a substitution of that something for the variable. It's a consistent substitution. So every single place you see an n, if you're going to substitute something for it, every single n has to be replaced with that. Or at least you can't replace two n's with different things. You might substitute for only some of them, but it has to be a consistent substitution when you do make the substitution. So these are variables in the language. For example, English. used to talk about a language? So, and that example might be, for example, knots. Now, what does it mean to say that knot is a language? Well, I'm not going to say formally what a language is, but languages consist of sentences, maybe phrases. You can use either word. And knots really are syntactic objects. You can think of knots as strings. And some rules about how to form those strings, the formation rules for knots constitute a definition of a language. That's just a sentence. So I'm not going to tell you what a language is in general, but let's just say that knots is a language. All knots that are syntactically valid, along with the idea of the rules that specify how to form knots, that together goes into the definition of something called a language. And we're talking about that language, the language of knots, in English. And the language of knot is really limited. You can only really have Z, S of Z, S of S of Z. You don't have more complicated sentences. You don't have variables. So the N that appears in it is certainly not a variable in the language of knot. The language of knot doesn't have variables, but it's a variable in the English language, which lets us do something like take this rule and substitute things in it to get concrete instances that say something meaningful in the language of knots. So now if you look at these green boxes, the contents of these green boxes are now things in the language of knots, although sometimes they may be just strings and not well formed. Okay, that is a lot of words. Does anyone have any questions to clarify this notion?
That makes sense.
Okay, good. So I think the most important points to take from this is that at risk of confusion, you must, to reduce it, you must always remember that the symbol N is never actually a part of anything that is a knot. But we do sometimes use it as a variable in English, thus a metavariable. Okay, so that's the first clarification. And the second clarification, well, not a clarification, it's a nice construction that lets us talk about definitions like this. And that construction is called a grammar. And you'll be seeing a lot of grammars in this class. Have I spelled grammar right? I have, good. So I'll tell you what the grammar is for the language of knots. The language of knots is defined by the following grammar. And if you look at the notes, there are certain words that are italic. I'll write those in a different color when writing on the board. And I'll explain what those are and what they mean. I'll give a more detailed explanation now than I gave in the notes. But in the next module, we're going to do this again in even further detail. So the green things, actually, I'll continue this. Green names are what are called non-terminals. So a non-terminal is never part of the language that you're describing. It's this thing in the language of grammars that lets you generate sentences in the language that you're describing, but they're never actually part of the language. And in the notes, these are italic. Now, non-terminals are not metavariables. And the simple reason that they're not metavariables is that variables suggest that if you substitute something for them, you make a consistent substitution. The nats on the left-hand side and the nats on the right-hand side are different. Mean a different thing. Now, the definition of nats, to write it again, we had one, that Z was a nat, and two, if N is a nat, then S of N is a nat. So this grammar, if you were going to read the grammar out loud, you would read something that's approximately exactly this definition. Specifically, what I would say is a nat is either Z or S of a nat. And I can write that down. And so this is how you read the grammar. Now, how does a grammar actually generate the things which are nats? Well, that's something that I'm about to describe informally. In the second module, we'll actually discuss this in greater detail. Now, this bar here and the equal sign, I've written them in red because they're neither non-terminals nor objects nor symbols in the language. They're just part of this auxiliary way that we write grammar definitions. And the bar is read as or. Now, these two options, 1 and 2, they're called variants of the definition. So 2 variants. And an important part of the definition of nats, but not of grammars in general, but of almost every single grammar that we'll encounter in this class, apart from examples that I'll give otherwise, we can always tell which of the 2 variants a nat is. So in other words, if you have a nat, it is either Z or S of Z, and it's only one or the other. It's possible to tell the cases apart. Now, that's why, well, things of the form S of nats have a open parenthesis and an S in front of it. Things of the form Z are literally Z and just that. So baked into this definition, it's very clear to us that if you have a nat, you can tell which one of these 2 variants of the definition of a nat that nat satisfies, right? So we'll see grammars like this. And probably the most important thing to note is that if I were to read this definition of a grammar, what I would say is a nats is either Z or S of a nats. Okay, we're going to discuss grammars in much greater detail later, so you don't have to fully understand how it is that how is it that a grammar corresponds to a definition of nats. Now, the next thing that I want to mention is this idea of universes. And the way that I motivate this is, let's suppose that we're doing the analytic procedure. Let's suppose you hand me something and you tell me that it's a nats. And then I myself am going to determine which one of the two variants it is. So I ask the question, is the thing that you've handed me Z, or is the thing that you've handed me S of something? And now let's say that you hand me a basket of apples. Then is a basket of apples of the form S of Z? What do people think?
No.
Or what? So you would answer to that question as no. Now, do you think that it is meaningful, or can you discuss how meaningful it is to say no in that situation?
It means that
Well,
we're
a basket of
supposed-
apples doesn't consist of characters.
Right,
know.
so that's one. Well, so would you say that the answer is a clear no, a meaningful no?
Yeah, I would say it's meaningful.
Okay. Now, what about a piece of paper which has pen strokes on it, which say S of Z? Is that
That's kind
a
of vague.
nat? Yes. And then in a lot of the situations, it can get even vaguer, right? So
Yeah.
if I'm supposed to tell which one of the two forms it is, then it might be very philosophically unsatisfying if I have to say it for every single possible thing that you could throw at me in the universe of all possible objects existing or imaginary, right?
Mm-hmm.
And so that's why we're not going to try and give a meaningful yes or no answer to everything. We're only going to classify nats as strings. So the question of is something of the form S of Z or is something Z can only be posed meaningfully to a restricted universe of objects. And that restriction, what universe we're going to choose to pose it, isn't something that's going to be somehow vaguely philosophically determined. We're going to start by specifying a universe, and we're going to stick in that universe. And then vague questions like, well, pen strokes on a piece of paper, is that in that universe? We won't have to rule on that. Our universe at the start will say, no, it's not. These are the only things in the universe, right? So do people see why that's something that might be desirable?
Yes.
Okay, good. So then the motivating question for universe is the question of is something the form S of something is only meaningful for some types of objects. So for example, strings. Now, what are strings? Strings are sequences of characters. Now, what are characters? You can say that a character is anything, in other words, any existing object, but then you sort of run into the same problem because how do you compare for equality of characters? That becomes a bit vague. So your universe should also consist of a restriction of what characters are. You might want to restrict it to just the characters that appear in your problem, in which case, remember last time when we looked at something like S of Z17, and there was an answer saying, well, this isn't a NAT because the characters 1 and 7 don't appear in any valid NATs. So if you started at the beginning by making your universe not consist of character 17, then you would outrule the question of, is this of the form S of something as outright meaningless? So that's one thing that you can do. But let's just say that we're going to stick with characters as all Unicode characters. Let's imagine that our strings are on a computer. They don't have to be. In fact, computers can only contain strings of a bounded length because they have memory restrictions. But let's suppose that we also fix some universe of what characters appear in strings. And so a natural universe in which NATs live is strings. And what restricting yourself to a universe means is that when you say anything, when you say consider a thing, consider an object, it's an object in that universe. And that universe, all objects in this universe might have nice properties. For example, if you actually want to implement this on a computer, then the computer would have a meaningful program for determining whether something is equal to Z or of the form S of Z. That predicates, that condition can be implemented very concretely for your universe, and you don't have to consider it for anything else. Now, then strings let you answer the questions. Is something Z or is something of the form S of Z? But I also argue that there is a more general universe in which you could consider those questions. Now, we don't have to work in that universe. And I mean, there are trivial ways to expand it. You could somehow make a definition of what meaningful things are when written down on a piece of paper. But we don't want to go in that direction. We want to go in this direction of, in the analytic procedure, we could ask, is something of the form S of Z or is something of the form Z? So if you just consider that process of asking questions, the answers to those questions, imagine the situation that the answer is always, so you have some object and you ask, is it of the form S of Z or is it of the form Z? And always you find that it's of the form S of Z. Then you look at the thing on the inside, you assume that it's a NAT, which form is it? And then you find that it's of the form S of Z again. And then no matter how deep you go, it's always of the form S of Z. It never bottoms out at a Z. So what happens if, consider let's say N is an object of the form S of N. It's S of itself. So for example, you could write something like it is S of S of S of dot, dot, dot. Now, this isn't a string. I mean, on one hand, it contains an ellipsis. What does that mean? But even if we thought of it as being an infinite string, you'd have to have closing parentheses. And where would the closing parentheses start? So strings are by definition finite, but I can sometimes say the word infinite string, which expands strings to being not necessarily finite. Well, this, even if we make sense of infinite strings, is not an infinite string. But I argue that there's a way to make this definition sensible. And now, so is this a nat? Let's imagine that we have a universe in which this makes sense. What do people think? If we have a universe in which this makes sense, is it a nat or is it not a nat?
I would say no, because you would have to get Z at some point, but it doesn't look like you'd ever get there.
So before, we had a process of showing that something is a nat and a process of showing that something isn't a nat. So apply that process of showing something isn't a nat here. What happens?
Well, you'd have to keep decomposing it, and only once you've reached Z at the bottom, you can make a decision, but you
Right.
never really do that.
So you fail to show that it's not a nat.
Yeah, I guess you can't say either.
And you obviously can't construct it because everything that you can construct is finite, right?
Right.
So before we had this property of, we had these two rules, and we had this really comfortable situation in, oh, these two rules make total sense because any string that you give me, I can apply those rules and I can rule on the case. Is it a nat or is it not a nat? But in this case, you can't show that it's a nat and you can't show that it's not a nat. So suddenly there's a gap between what you can show to be a nat and what you can show to not be a nat. They don't reach up, and there's things in the middle. Now, this is a super pathological example that you don't have to understand and that we're never going to return to in this class. But this actually says that if you have a recursive definition like we had before of nat, there are two ways to interpret it. The first is as what is called an inductive definition. And in the inductive definition case, it's a nat is anything that you can show to be a nat. So by the inductive definition, is this S all the way down object a nat or not?
No.
Yeah, exactly. Now, the other definition is the co-inductive definition. And you can write this as a nat is anything. Again, anything always means in the universe that you can't show not to be a nat. So someone else say in the co-inductive definition is this S all the way down object a nat or not?
Yes, because using either analytic or the synthetic method, you can't make a decision. It will never terminate.
Oh, yes, exactly. So it is a nat. Good, because you can't show that it's not a nat using, yes, precisely. And another way to write these definitions is that you can say a nat is anything that you can create. And then here, a nat is what you can't destroy.
So can you have anything that's in between where, well, like in the example, where you can't create nor destroy it? So is there ever like a weird limbo place for it?
Oh, well, you can either destroy something or you can't destroy something, right?
Yeah.
Well, then if we're working in the co-inductive setting, that tells you whether something is a NAT or not, right? Because you either can destroy it and then it's not a NAT, or you can't destroy it and then it is a NAT.
Oh, so you either choose to be inductive or co-inductive. You can't be simultaneously both.
Yeah, exactly.
Okay.
So as an example, this S all the way down thing, whether it's a NAT or not depends on which one of these two choices you make. So it's ambiguous. So then you have to actually make a choice. So yes, to rule on S of S dot dot dot, you have to choose one of these.
Okay, that makes sense.
Now, this is a really pathological case. In this class, we're always going to look at inductive definitions. Now, in the notes, I call this a recursive definition. There are two very different things that count as a recursive definition. Here, we're recursively defining a category, or we're recursively defining some class of objects. We're recursively defining what NATs are. We're not defining a specific number, a NAT like Z or S of Z. We're defining the class of them. So we can call this as a data definition, or a type definition, or a data type definition. Now, I haven't chosen a specific word yet, but there are going to be recursive function definitions, and those are going to be different because there you're actually defining a concrete piece of data, the function, as opposed to a class of objects. So here, when I talk about recursive definitions, I do really mean something different than recursive function definitions, which we'll come to later. Okay, so that was a bit of a tangent, but what I mean to say is, going back to this class, in this class, recursive, let's say, data definitions are inductive. So in particular, for NATs, this means a NAT is anything that you can show, that you can construct by a finite sequence of applications of the rules, by applying the rules finitely many times. Now, the question of whether inductive or co-inductive definitions are the same thing depends on the universe. So for example, before I argued that if you were working in finite strings, then there's no gap between them. That's you can always, if you take any string, rule by the rules whether it's a NAT or not by just applying them finitely many times. Does that make sense to anyone? Or if it doesn't, can you please ask a question for clarification?
I'm sorry, I can't read the word. Is it finitely or infinitely?
Finitely, let me rewrite that. Well, okay. I mean, you're talking about this word at the bottom, right?
Yeah.
Okay, yeah. I'll rewrite it. Unless I've misspelt it. Have I misspelt it? Is there an E? I think that's right.
I think that's right.
Okay. Now, here's the other idea that I'm going to introduce. Okay, so first off, this pathological object with repeated S's, we're not going to encounter it again, except for one other thing that I'm going to say about it in this section. And you don't really have to worry very deeply about inductive or co-inductive definitions because we're going to always look at inductive definitions. But I did want to show you that sometimes there is a gap between them and that we actually did have to make a choice to work with inductive definitions as opposed to co-inductive definitions. So that's a detail that's good to know. And that I don't want to have be something in which you're misled about believing otherwise. But it's also not that crucial for everything that follows. So I described that in the notes in some greater detail as well. Okay, so now I want to show you a universe that's different from strings and that's actually much, much easier to think about than strings. And I finally get to answer the question of why did we have all of these parentheses inside of the S's? So here's another universe. And this answers the question of why all the parens. Now, how to motivate this is that when reading this thing, what words did I say when reading it? How did I read it? Anyone?
S of Z.
Yeah. So I said of this thing, and of sort of sounds like function evaluation a bit, but S of, and then S of Z, or I can sort of put brackets here. Well, if we think of, for example, 2 is the successor of 1, and 1 is the successor of 0. Now, I'll just cut to the chase and I'll show you one way that we can think about this. I can draw something called abstract syntax trees, abstract syntax trees. So I would think of S of Z as S of Z. I draw it like this. Now, what are these? So I'll write down the name of these. These are abstract syntax trees. Or in other words, AST. Now, in this class, a tree has so it has two things. It has nodes, and these nodes are always labeled. And the other thing that it has is edges. Now, an edge always connects two nodes. So this is what I mean by a tree. Now, abstract syntax trees are a special type of tree called a rooted tree. Now, what does this mean? So for example, I'll label this AST for S of Z. The thing at the top of the tree, that is the roots. So in computer science, frequently we adopt the opposite convention of nature. In nature, trees are rooted in the ground, right? But in computer science, the root is at the top because you read a page from top to bottom. So it's more natural to read it like this. So that's the roots. Then these are, for example, edges. So the root is always a node of the tree, and then you have edges connecting nodes to nodes. Now, in rooted trees, every single edge has an interpretation of a parent-child relationship. So what does this mean? This means that in here, S is the roots. S is the parent of S of Z. 2 is the successor of 1. 1, in turn, is the successor of 0, right? So in every single edge, you can make sense in the context of that edge, which one of the two nodes that it joins is the parent and which one of the two nodes that it joins is the child's.
Question: why are we mentioning 0 and 1?
Right. So good. I said S of Z is S of Z, right? And we also had this idea that nats are a model of numbers. So in the world of numbers, the thing that nats are modeling, 2 is the successor of 1 and 1 is the successor of 0. That's not a statement about nats, but that's a statement about numbers.
Okay.
But from the start, we also think in some way that nats were made to model numbers.
Got it.
So there is an analogous statement about numbers, or at least there isn't. It's not so much a statement about numbers as I think it might be something that provides a useful picture of the language that I'm using.
Edges can also just be referred to as the branches of the tree, right? Or is it?
I do not like the word branch. Why? Why? I think the word branch might have a technical usage that refers to a bit of a more complicated substructure in a tree.
Yeah, I just remembered when I took finite mathematics, we learned about like the structure of tree graphs, like using
Yes.
computer science, and that was the term the professor
Okay.
used.
Okay, that might happen. I think in this class, I will not use the word branch in any way.
Okay.
Okay, I'll call them edges. In almost every single discipline, sometimes words have conflicting meanings, right? Sorting out what notation you use, you just have to, you follow the predominant convention, but sometimes you also have to make a call on what's, if there's ambiguity, this is what we're doing. So these are edges.
If you were to water an abstract syntax tree, would you water it from the top or the bottom?
From the top, precisely.
Okay, thank you.
Right. Okay, now here's another thing. What is the root of a tree? There's one more thing. If you think of parent-child relationships, then the reproduction is asexual in the sense that every node has at most one parent. I mean, in human biology, there are two parents. But here, if you are a node, then if you have a parent, you have at most one parent. And then what is the root? I said at most. Only the root does not have a parent. So that's in a certain sense where the tree starts. And another convention that we can use is that nodes without children are called leaves. So I'll highlight the words that I defined here. So I defined a tree. Trees have labeled nodes. I won't say the word labeled, but I'll just say nodes. But nodes aren't just, they have a label on them. So the S's or the Z's. Then I defined this idea of a parent-child relationship. Then I defined what the root is. A root is the only node which does not have a parent. And nodes without children are leaves. So I'll give you 20 seconds to look at this definition, and then I'll label those things on the tree above.
Question. The edges represent the parentheses then?
So I'll explain this connection. That's the next thing. So I'll explain exactly the answer to that in a bit. Okay, so let's look at this tree. So the root is S, and we always conventionally draw the roots at the top. Now, every single node that is not the root has a parent. So if we look at, for example, this S, it has to have a parent. Also, if you look at this edge right here, this edge right here represents a parent-child relationship. So one of these two has to be the parent, but the root does not have a parent. Therefore, in this edge, this S is the child. Now this S has a parent. So if you look at now this edge, and you ask who's the parent and who's the child, well, S has to be the parent because S already has a parent, the top S. So in fact, just by specifying who a root is, you also know for every single other edge in the tree, who's the parent and who's the child. Specifically, the simpler way to see it is that things above are parents and things below are children. Now, actually, there's a thing that I said, which I really don't want to say it. In this parent-child relationship, I said that this is the parent of this S. Actually, the way that I'd like to think about it is that this S is the parent of this entire subtree. The child's, okay. Okay, I don't have to force that definition. You can think of maybe it being this, but what S spawns, the descendants of S are really a subtree. It's S and all of its children. Okay, that's not a hard definition. You can also think of just the nodes as being children in a parent-child relationship. Yeah. Okay, I said you can either think of it like this or like this. That's bad, but this isn't something that I want to rule on definitely. But I do want to have in your mind that the ancestors, the descendants of S aren't just the single S below it. S in turn has children. And you can think of the top S as containing everything inside of it. So for example, specifically, since this AST is something which we're going to discuss later, I mean, immediately after this, this is supposed to somehow represent S of Z. The thing that the first S is the S of isn't just the second S. It's the S of Z. The S of Z is contained inside of this S. Well, containment is sort of a different thing now, as from a parent-child relationship. But you should think of the S of Z as being inside the top enclosing S. Oh, and okay, one more thing. So in this tree, the Z then is the leaf. This is the leaf, the only leaf of the tree. This has no children. There's nothing below this Z. This S is the root. There's nothing above it. There are no parents. And then for every single other edge, the thing on the top is the parent and the thing at the bottom is the child's. Any questions? So I'll give you another example of an AST. Now remember that right now we're not talking about numbers. I mean, I've said a few things about numbers, but really this module is about nats. So an example of something that's not about nats and that we're not going to discuss for the rest of this module is arithmetic expressions. With numbers. So again, not the topic of this module. And so I wanted to do this example because it is an example of a tree, an AST, in which there are multiple children. So you can talk about, for example, adding together two things. What are those two things? Well, the first is going to be 2 times 3. And the second is going to be, let's say, minus 1 minus 6. So this is here to label it. The blue isn't actually part of the tree. This is the roots. It's at the top. These things at the bottom are the leaves. And then here are two other nodes, times and minus. Those two nodes are neither the root nor leaves. They have parents and they have children. And something that we'll get to later, if you thought somehow of the tree right here as representing S of Z, then you can think of this tree as representing plus, now written as a prefix as opposed to an infix operator. You're adding together the product of 2 and 3 with the difference of 1 and 6. So close this paren, and then that closes the paren of the plus. Actually, I'm about to discuss how you go between one of these and the other. Now, one thing that you see is that if you have, for example, 1 minus 6, that's different from 6 minus 1. So that suggests that in a rooted tree, the order of the children is important. So 1 minus 6 does not equal to 6 minus 1. In other words, the children of any node come with an order. So we're not going to return to arithmetic expressions in this module again, but this is a good illustrative example where you have multiple children in general. And as another illustrative example, here's something that you're not allowed to have. So not allowed. Let's say you have S, and then you have two children which are both S, and then you have one, and somehow this is a child of two different parents. So that looks like a cycle, right? You don't have these. Trees don't have cycles. And the property that trees don't have cycled is prevented by the rule by which a node has at most one parent. So you can't have cycles. And for any of us, for example, if we look at our family tree, there are going to be lots of cycles because history is very long and a number of ancestors that you have goes up exponentially in generations. So the tree of ancestors is not a tree in computer science sense. Ancestry trees are not trees. I'll write human ancestry trees. If you look at bacteria which reproduce asexually, then their ancestor trees are actually going to be computer science trees if you represent them in data. I'll just make this very big. Okay, now I'm going to explain the connection. Oh, by the way, any questions here?
So is this how
Okay,
you make
so-
like compilers?
Oh, yes.
Like, do they use
Compilers work on syntax, right? They do a lot of syntactic analysis. You definitely have a bunch of this in compiler theory. This is the way that you visualize syntax. So this is one of the most important concepts in CS, and definitely its place in compilers. In this class, we're going to actually see a bit of interpreters. It's in brackets. It's a language that can read itself very easily, and you can write an interpreter for it. So we'll see that, but not compilers in this class. Okay. So what's the connection between these two things? And that connection is via something called S expressions. Now, notice that we had, if we looked at this tree S of Z, and we associated to that S of Z, then what we had is that this was an expression with parentheses. And then the first thing in the expression was a label. And that label went up here. And then we drew an edge to each of the expressions contained in it. And so if you look inside, you have this expression. And now you take that and you turn that into a syntax tree. And then it has a label at the front. And you put that label here. And then it bottoms out with this Z, which becomes this. So that thing is a squiggly arrow. I should probably redraw that. Whoops. Now, what was important here? The way that we read this is we had these labels. Everything was an expression at the top level. Well, at the top level, we can also have something like Z. Z represents the tree just Z with nothing else, right? So an S expression doesn't always have to be an expression with parentheses. It can just be a label. But if it is an expression with parentheses, then it begins with an open parenthesis, it ends with a closing parenthesis, and the first thing after that closing parenthesis, not divided by white space, is going to be the label that we're going to put at the root of the tree. And then everything following it, we're going to have some number of S expressions. Then we're going to take those S expressions individually, turn them into syntax trees, and then draw from those syntax trees parent-child relationship of their roots to the label that started this tree. And then if we just have labels, we represent them with the syntax tree that's just that label. So I can give you a grammar for the language of S expressions. So here is grammar, a grammar. Now, again, I still haven't discussed formally how grammars generate something, although I did give one more detail. A grammar is an inductive definition. A grammar specifies rules for how you can build something up, and then the things that it actually classifies, the language that it generates, are everything that you can build up by finitely many applications of the rules. That sounds formal. I mean, to make it formal, I'd actually have to go into set theory about what the sets of things that it generates are. So that's one level of formality above the level of formality that we currently have. But okay, so just a grammar for S expressions at the level that we've been talking about it before. So there are lots of levels at which you can understand it. And you don't have the deepest level right now, but that's fine. So if you think that something isn't sufficiently rigorous and there are missing details, and that's good. It's good that you think that there are missing details because there are. Okay, so the non-terminals are going to be SEXB. I am going to define what the S expressions are. Now, what is an S expression? An S expression is either a label, and label is also a non-terminal, or it's going to be something. Now, I don't know where to draw the closing parenthesis, but so I'll have to switch colors again. Or it's open parenthesis, a label, and then it is some number of S expressions. Now, how do I say some number of S expressions? Well, first off, I want there to be at least one S expression. And then I want to say that after having one S expression, so I can't have just open parenthesis label close parenthesis, because I prefer to use the first variant instead. We still want our variants to be distinguished. Actually, for NATs, and here, the property of being able to tell which one of the two variants it is, I called it in the notes that the variants are mutually exclusive. It's clear that which one of the two it is. Actually, no. For this grammar, they'd still be mutually exclusive. But the problem would be that if you looked at the trees that they represented, you wouldn't know, for example, if for this tree at the bottom, whether this tree corresponds to the S expression Z or open parenthesis Z close parenthesis. Okay, that was a bit of a digression. So the way that I write this grammar is like this. And then I write a dot, dot, dot. The dot, dot, dot is also part of the language of grammars. So it has its technical meaning. Now, this grammar isn't complete because I haven't told you what labels are. And labels I'm going to sort of define in a way that exits the grammar. I'm going to say that a label is anything that makes sense as a label. So that's sort of like exiting the language of grammars. I'm going to specify in English what this means. Okay, let me explain what the dot 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 means. So in a grammar, dots, you know what? It's not, oh, but it's, I could draw it in a different color. I could draw it in green to indicate that it's like a third different type of thing. So dot dot dot, which is called an ellipsis. Means 0 or more of what precedes it. So in other words, I could tell you then exactly, concretely, what this means. So for nats, for example, we had a grammar, and the grammar had two variants. A nat was either z, or a nat was s of z. Those are two variants. When you have something like ellipsis in a grammar, it turns the variance which it's discussing into an infinite family of variants. So if I were going to read this grammar out loud, what I would say is that I'm not sure if I put an end there, a S expression is either L, or here, I'll use metavariables for labels, is either, okay, no, I'll write this, is either blue label no, I'll write it like this, is either L, that's hard to see, I'll write it like this, L, or of the form L, and then I'll write T subscript 1, or of the form L T1 T2, or of the form L T1 T2 T3, or so on. Now, where L is a metavariable, standing for a label, and the X sub I are and the T sub I are metavariables standing for S expressions. So again, what does this mean? That's a bit of a mouthful. What I mean to say is, well, remember before when I said in a grammar, the non-terminals are not metavariables. So for example, if you use this ellipsis, an ellipsis says 0 or more S expressions. Then for each of those options, 0 S expressions, 1 S expressions, 2 S expressions, you can sort of think of that as a different variant of this rule. So there's really an infinite family of variants. The choice of 0 S expressions gives you a thing of the first form, LT1. Why is there 1? because that's the reason that I wrote S expression followed by S expression 0 or more of. This trick of writing something and then writing it again and then putting an ellipsis lets you get one or more of. So that's just a bit of a hack in order to do this in the way that grammars are specified.
I have a question.
Yeah.
Is L equivalent to open parenthesis, L close parenthesis?
That does not exist in the language of S expressions because the second variant has to have at least one.
Got it.
So that's
then
precisely why it's one or more of.
Okay, because
now
why? That is 0 or more of.
Right, but I have, yes, that's why I've written S expression twice.
Oh, okay, got it. Thank you very much.
So writing it twice turns, S expression means immediately what precedes it. So this ... applies to this S expression, and I choose 0 of this, 1 of this, 2 of this, but then there's +1 to all of them. So now it's 1, 2, or 3.
Got it, that makes sense.
Now, why also to answer the other question, is Z equivalent to open parenthesis, Z close parenthesis? Well, both of those would look like this tree. And I want an S expression to correspond to a unique abstract syntax tree. I want there to be a direct translation of ASTs to S expressions. And if I allowed for there to be 0, S expressions following a label in parentheses, then both of these S expressions would correspond to this tree. And I want uniqueness, so I just prevent it by doing one or more. Now, again, I haven't defined grammars formally. I've defined them formally at some level. And I haven't described abstract syntax trees formally either. I've given this description, but this description isn't fully formal. For example, a fully formal description would be specifying a universe and then specifying what in that universe constitutes an abstract syntax tree. Again, that's a level of formality above the level of formality that we're talking about. Any discussion has a lot of different levels at which you can discuss it, and we don't have to stick to the most formal level. I guess this is me saying, don't worry about the details. And I keep saying it over and over again, and you probably aren't worried about the details. So it's probably redundant. Okay, back to where I was. So at the level that we're discussing, I claim that there is an exact correspondence of S expressions to abstract syntax trees. Oh, before I do that, I also want to say is what a label is. Well, we want the variants to be mutually exclusive. In other words, we want the first variant to be distinct from the second variant, or more strongly, we want each of the infinitely many variants in the second family of variants, so of which I've drawn 3 examples. Here are 3 examples. I want to be able to tell in this infinite list of examples, plus this leading example, if I have an S expression, which one of these it is. I want there to be no ambiguity. Now, where could there be ambiguity? Well, for example, if labels had parentheses, or if labels had spaces in them, right? So in order to say what a label is, in order to avoid ambiguity, I say that a label has neither parens or white space. And I guess there's one more condition, which is not vacuous, but a label shouldn't be empty. So this condition is to ensure that I can tell which one of the variants it is. Okay, so I've said a lot of high-level things there. And it should be clear at some level, but then there's also a lot of chance for confusion. So I like to give everyone a chance to ask questions. If something's unclear, please ask a question. Don't worry about taking it off track. I want to answer. I want everyone to have some understanding. Go.
Question. What's that like half arrow thing before like the brackets after SEXP?
Sorry, in the grammar? Or
Yeah, in the grammar. What's that half arrow thing? Like the downward pointing.
so
half
that's
arrow.
a dot dot dot. You're talking about the green thing here, or where?
No, not that. Like the thing to the left of the start of the parenthesis.
Ah, yes. Should be a bar. So in grammars, when we have multiple things that define a label. Oh, actually, what did I do before? Before, for the grammar for NATS, I wrote the things that are actually in the language, the parentheses, in a different color, didn't I, right? Whoops. Right, so I wrote them in blue there. I should be consistent. And since the actual parentheses represent actual characters in the universe that we're describing, I wrote the non-terminals in green. Okay, that's bad. Okay, the color conventions here are completely different from the color conventions that I had before. I'll choose a different color of red. More specifically, the equals and the bar are just auxiliary things to indicate variance in this grammar definition. The parentheses are actual characters in the language. All of the blue things are non-terminals, and in the grammars, in the notes, they appear in italic. They don't have color, they're just italic. And then the dot 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 is a special grammatical construction, and I put it in green this time.
Okay.
But the bar does not mean something either in the language or a non-terminal. It just means the second thing an S expression can be is that thing.
Should I interpret the vertical bar as an exclusive OR in this case?
Yes. In all the grammars that we'll define in this class, they will mostly be grammars that are S expression grammars. So for example, if you think about the definition of NATS, NATS are S expressions. So yeah, that's an example that I should do. And S expressions are exclusive or for the variance. Well, I mean, S expressions sort of in computer science terms, these are words that are going to be unfamiliar with you, but S expressions are the simplest way to ensure that a grammar has a unique parse tree. There are some people, maybe one or two people in this lecture for whom that's meaningful. But for everyone else, don't worry. But roughly, S expressions are a very easy way to guarantee uniqueness. Now, NATs are S expressions. If we looked at their grammar, a NAT was either Z or it was S of Z, where, S of NATs. Where here we're doing this leaf definition where the S expression doesn't have anything, or it's something where you have a label followed by an S expression. And then to give another example, before I drew this arithmetic tree. Plus, I don't remember what the exact numbers were, it doesn't matter that much. 2, 3, minus 1, 6. That may actually be the exact numbers. Then as a S expression, the label at the top is a plus. Then this has two subtrees. That's a new word that I'm using, subtrees. What are you adding together? You're adding two things. What are the summands? The first summand is itself an S expression. It's the product of 2 and 3. And the second summand is the difference of 1 and 6. This is prefix notation. The operator goes before the two arguments that go into an operator. But prefix notation has the advantage of easily being translatable into a syntax tree. So this is an AST, and this is an S expression. And my claim is that for ASTs exactly corresponds to S expressions on the nose. And I'm going to justify this at the intuitive level that I have before. I'm not going to prove it right now. We haven't discussed proofs yet. But if anyone doesn't see why that's the case, I'd really like to explain it to you. So ask.
I'm just a little bit confused. What's the distinction between a label and an S expression if they're equal to one another?
Oh, so it is possible for an S expression to just be a label, like Z. So that type of S expression would correspond to a tree that doesn't have any edges. It just has the roots.
Oh, okay.
But S expressions are more general. S expressions can also include this form of structured data. So S expressions can also have children.
So at minimum, they have to be the label and then can be bigger than that later.
Yes.
Okay.
So for example, all trees have a root. A tree can't be empty.
Yes.
And an S expression can't be empty either.
Oh, okay. So that's the only reason why the S expression is equal to the label, right?
Yes. Technically, I could have made it be open parenthesis label and then 0 or more of. Then I wouldn't need the first case. But then I could actually remove this, and then I could have open parenthesis Z close parenthesis. But when we talk about rackets, the grammar of racket is going to be S expressions, and they're going to have this thing available.
Okay, got it.
So I would like bare labels.
Okay.
Oh, so the programming language that we're eventually going to look at, everything with some exceptions that will only become relevant later, is going to be an S expression. So for example, if you want to do arithmetic in that language, the way you'd write it is like this. Okay, really, that took way too long. I didn't get anywhere to where I needed to. I'm going to have to push back the homework to a later date. Can we take, let's take a 5-minute break. And I have until 3:45, right? Is that right? That's the end time of this lecture? It should be, right?
That's correct.
Okay, let's take a 5-minute break, and then I'll start defining addition. I still won't explain how to prove things today, but it will definitely going to get there next class, in which case I'll push the homework to be due on Saturday instead of Friday. But let's take a 5-minute break. A 5-minute break is way overdue at this point. Again, sorry, I totally lost track of time. I guess I didn't know how long it would take to discuss this. Anyway, less talking, more 5-minute breaking. Back at 3:20.
Can I ask a general question?
Yeah, go ahead.
Is there a grammar for writing grammars?
Yes, there is. Yes, yes. Yeah,
Can
definitely.
you write that grammar using the grammar that we have?
Actually, wait a second. Grammars, in order to be valid, also satisfy some rules. For example, no. Actually, the answer is no. Why? It's a very subtle reason. So, for example, let's say that I defined nats. This is a non-terminal. And then I wrote that nats is equal to something like a non-terminal. That's cats. And now the problem is that the non-terminal cat hasn't been defined anywhere. So I've used something without defining it, and I never give a definition. Then that grammar doesn't make sense because I don't have no way to interpret cats. So that's this type of thing where you can only, if you use something, you need to define it. That's actually something that's not, again, in CS terms, context-free grammar. That's a context-sensitive grammar. And grammars, in this way, these are called Brachis normal form grammars, only specify context-free languages. If that doesn't mean anything to you, then that's fine. If it does mean something to you, okay. I guess a more down to the earth explanation is that there is a grammar for specifying grammars if you don't care about rules, like you can only use something that you define. If you do want rules like that, grammars can't capture that.
Okay, that's going to be something to think about. Thank you.
Right. Okay. I'm also going to take a break now. Oh, okay, there we are, 321. Has anyone thought of any questions to ask? Oh, and do people hear me? I think they should. Nothing's changed, right? Okay. Yes? Can anyone say yes?
Yes.
Good. So I'm going to do a very, very quick recap of what we did because that was long. I think I probably lost people's attention at some point there. Where is my pen? Here we are. So as a quick recap, we started to discuss what does this definition of not mean? And then this was a very long digression into syntax. We said that the definition could be captured by a grammar. And before we said that it could be captured by a grammar, we clarified that when you had statements like if n is a not, then s of n is a not, then the n there isn't actually a symbol that appears in any legally valid knots. It's a variable in the English language used to describe ways that that sentence can produce more concrete rules that actually describe sentences in the grammar. So metavariables. Then we had grammar definitions. In grammar definitions, we had non-terminals, which were different from metavariables because the knots that appears on the left-hand side and on the right-hand side of this equality mean different things. Now, grammars really are just a way to encode rules like we had before. This grammar, if I were going to read it, I would say that a knot is either Z or S of a knot. Now, when you have rules like this, how do they define objects? Well, we discussed that there were two definitions that in certain edge cases could mean different things. The first is a knot is anything that you can show to be a knot using applications of these rules. And that is the inductive definition. And in this course, a grammar always defines the collection of objects that it describes, in this case, the knots, inductively. The other option was a co-inductive definition, in which case it's everything that you can't show is not a knot. Now, I'll give just one small digression. I keep doing digressions. Before, when I described this object, S of dot, dot, dots, it didn't make sense as an infinite string because the closing parentheses have to start somewhere. But it does make sense as an infinite AST. We can think of it as S of, it's a tree and then the children always descend downwards. So this makes sense in the universe of infinite ASTs. But not in the universe of infinite strings. Now, we will never work in the universe of infinite ASTs, and we won't use co-inductive definitions. However, the universe of ASTs, by which I mean finite ASTs, is in a certain way equivalent, which is what I try to argue, to the universe of S expressions. And since I'm reviewing, I should say what an AST was again. An AST was a rooted tree. What this means is that there is, well, first off, as a tree, it consists of labeled nodes and edges. The node which appears at the top of a diagram is a root, opposite to the way that it is in nature. Edges represent parent-child relationships. The thing at the top is the parent, the thing at the bottom is the child. Any node has at most one parent, and the root has no parents. Things which have no children, the things at the very bottom, with nothing coming out of them, are called leaves. Right, so that's what an abstract syntax tree is. And ASTs correspond exactly to S expressions. Now, S expressions aren't just all strings. In fact, if we want to go from the universe of all strings to the universe of S expressions, then we have a grammar for that. I guess the grammar isn't completely a grammar because we have this thing where, as a label, we describe it in English. Labels shouldn't contain parentheses and they shouldn't contain spaces. But ignoring that fact, from going from the universe of all strings, we can go to the universe of S expressions. And S expressions are really this very nice collection of strings. They're strings that have parentheses in the exact same way that nats had parentheses. And what parentheses really encode is this layered structure, that there's something on top and that thing contains things, and that those things contain, in turn, contain things. And then since ASTs are equivalent to S expressions, and almost every single grammar that we'll look at in this class will be a grammar that makes sense in the universe of S expressions, as opposed to the universe of strings. That is, the universe of S expressions is a smaller universe than the universe of all strings. And the NATS definition can be taken as a grammar not just in the universe of strings, but more restrictively in the universe of S expressions. And it's nicer when we get down to a more restricted universe. Well, when we restrict ourselves to working with S expressions, we can think instead of symbols on a page as pictures of trees. And in a lot of ways, thinking about them as trees makes it much more intuitive to reason about what's going on. We're going to draw a lot of pictures in what happens next. And the way that the pictures correspond to strings of symbols is by this correspondence that I sketched above. And if anything's unclear, my notes are a really good place to turn. And this lecture is recorded, so you can turn there. Okay, so that was my recap. Any questions? Okay, the next topic, I'm starting to rush because, well, okay, I'm going to push back the homework. But the next topic is defining plus. So philosophically, why did we get here? Why were we considering this? We had a model of numbers as apples in a basket. And when it came to that, we had a definition of addition. What was our definition of addition? One basket, you had another basket. You counted the first basket, and then you started at the number that you got to in that count. And then you started removing apples from the second basket and incrementing that. So that was our definition of plus there. Now, because we have this thing in our brain called object permanence, it's clear to us if you shuffle objects around, the number of objects doesn't change. And that makes it obvious, problematically obvious, that A plus B is the same as B plus A. We'd like to justify that in some more substantial way, so we went to NATs. And now we talked about NATs. We said they're highly structured, and everything that we talked about today, it was actually an explanation of the way in which NATs are highly structured. And I guess the punchline was then we can see NATs as trees. We can see all NATs as being S of S of S of so on until you reach Z, or it can just be Z. Now, how do we define plus on NATs? That's our goal. Now, here I've prepared, so here, okay, here's a fun philosophical discussion. So I'm going to ask, so it begins with a quote that I found in a book that was published in 73, about someone criticizing new math. So new math was this movement in order to match the Soviets. We're going to introduce set theory into our curriculum. We're going to make it rigorous. Middle school students are going to be taught about set theory. So the US went all there. Actually, the book that I'm using for set theory Hallmosh's naive set theory, I have an edition of the book which has this really, really cute cover, which is a picture that was a cover of a new math textbook. So this picture sort of philosophically represents what new math is. Okay, anyway. And so in criticizing this movement, schools apparently didn't implement it well. This book begins with the following quote. The book actually starts there. Let us look into a modern mathematics classroom. The teacher asks, why is 2 plus 3 equal to 3 plus 2? Unhesitatingly, the students reply, because both equal 5. No, reproves the teacher. The correct answer is because the commutative law of addition holds. And the book is called Why Johnny Can't Add: The Failure of New Mathematics. Now, I mean, that's a good way to start a book, although I've looked to the author and he has books that argue that the publish and perish culture of mathematics is responsible for people talking about pure math, which is inherently wrong and nonsensical. So apart from that quote, his opinion is invalid. Okay. I mean, I categorically disagree with him, so let's say I ask you, what is 5 plus 13? And I want you to give the most useless answer that you can think of to that question. That's still an answer.
It's 13.
513.
Well, that's wrong. I want you to give an answer that's still correct, but only technically correct.
It's bigger than 5.
Oh, good. So one of the answers is it is bigger than 5. Right. So this answer highlights that the word is can mean two different things. Is can mean equality, or in the sense of something is something. But you can also say that something is red, which means that that thing has the property of being red. So for example, if you say this ball is red, it's impossible to conclude that red is this ball. Or in other words, the abstract concept of redness is the same as this ball. So that highlights one thing that I hadn't thought about the word is. But now suppose that we have a word is that is symmetric. So is means is equivalence to. So what's a useless answer under that interpretation of is?
Is it 13 plus 5?
Okay, yeah, good. So that's true. Okay, what are some other answers in this light?
5
It
plus
is the
13.
combination of 5 and 13.
Okay, that's let me write your answer like this. So that's another way to reword saying that 5 plus 13 is 5 plus 13, right?
Yeah.
Or the combination. Of 5 and 13. So yes. So and give me one more. There's one more that I can think of. So it's still a useless answer. So it's still not.
A number?
Oh, I guess that falls in the first category, except the other way around. You're saying yes. So or 1 prime, a number. So these are versions of is that are not symmetric. It's now it indicates belonging as opposed to having a property. So, but another one that actually now is symmetric. Okay, what I was thinking of, unless anyone can say it now. Okay, something like 12 plus 6. So they're different numbers, right? So here are a bunch of useless answers. The first one is useless for, and I hadn't thought about this one, or this one. They're useless because the word is in this case denotes something different. It denotes properties or belonging. And that's an interesting ambiguity in the English language. Now, if we ignore something like that, these things are the same as all of these expressions. It's the same as 5 plus 13. 5 plus 13 is 5 plus 13. That's not a wrong answer. Or you can flip them around. Commutativity. Actually, in that book, he goes on to say, when Johnny comes home, his father asks him, what is 2 apples and 3 apples? And he says, do you mean 2 plus 3? And then his father says yes. And he's like, oh, I've been taught that it doesn't matter if you talk about apples or oranges. 2 plus 3 is always 2 plus 3. Then but what is 2 plus 3? 2 plus 3 is 3 plus 2. So that's the way that introduction should use. Okay, let's suppose I want to ask a more pointed question. Let's say I don't want to ask any of these. I want to make those answers be avoided. What's a thing that I can ask that avoids those answers?
Evaluate 5 plus 13,
okay,
I'm
that's
sorry.
the final answer. Yes. Okay, the stage that is between these two is what is the value of? And can someone give me a useless answer to this question? What is the value of 5 plus 13?
Learning how to add.
Oh, very good. So that reflects an ambiguity in what the word value means. But okay, in this case, we mean value as something technical. But here's the, anyone else? So for another useless answer?
Positive.
Okay, that's in the first category. As in, that's having. No, the value, oh yes, the value is positive, right. I'll write that down. So that reflects the fact that I still have the word is, and the word is can still have this property or belonging thing, which I want to avoid. Okay, so what's another one?
The value of 13 plus 5.
Yes, good. Okay, but I believe our education master students gave the exact answer, right? And so it's evaluate. So the most pointed question, evaluate 5 plus 13. Now this question, as far as I can see, does not have room for things because the word is doesn't occur. You can say evaluate 5 plus 13 is 5 plus 13, but is didn't happen there. It's just an order. It's not so much a question as an order to evaluate 5 plus 13. And then I say, okay, answer is 18, finally. Can anyone think of, so I can't think of ways that evaluate 5 plus 13 doesn't get to you, doesn't force the only correct answer to be 18. Okay, I think, so if anyone comes up with one by next class, that's going to be interesting. But what did we learn here? This word evaluates. This suggests that if you look at things like arithmetic, there's some, I call these arithmetic expressions in CS terms, but expressions have a value. There's a way to simplify an expression, and eventually you get down to something, and that something is going to be a number, and that number is the value of the expression. So how the programming language that we're going to use works, this is just a bit of a digression again, is you would have things like 2 plus 3 plus 1 plus 7. And then the programming language would evaluate this by rewriting this as 6 and then 1 plus 7. Whoops. Sorry, times. Whoops. Okay, I'm getting off track. and then it evaluates this to 6 plus 7. And then it evaluates this in one step to 13. And then you'd be at an answer. And that would be the value of this expression. So in this section of the notes, I believe this is section 1.3, right? So we've only gotten to 1.3. I really want to dig into this notion of what it means to evaluate something and how can we see these steps of evaluation as something formal on expressions. So now we're going to be dealing with expressions. They're not actually going to have nested pluses. We're not going to think about nested things at the moment. But evaluation and values are the theme. So really all of programming and the books that I use, consult for this, describe it this way. They introduce the concepts as they would in algebra. You think of what a computer does as just doing algebra in the way that you're taught how to do algebra in school, evaluating things. So to answer the question about this new math question, the teacher said that 2 plus 3, y is 2 plus 3 equals to 3 plus 2. The student said because both have the value 5, because both are equal to 5. The teacher said no, it's because the commutative law of addition holds. But if you think about that, what does the commutative law of addition say? The commutative law of addition says for all numbers, a comma b numbers, a plus b equals b plus a. But what does it mean when a and b are specific numbers for a plus b to equal b plus a? What does that mean?
That they both evaluate to the same number.
Yes, exactly, that they both evaluate to the same number. So if you want to talk about the commutative law of addition, at the end, you still have to make reference to evaluation. But it's possible to answer the question of why is 2 plus 3 equals to 3 plus 2 without making reference to the commutative law of addition. You just evaluate it. So in some way, the answer of because you evaluate it is more fundamental. The commutative one requires that idea to be in the background. That's the only way you can make sense of the commutative law of addition. So Johnny was right. Johnny was more right than the teacher in that case. Right, what time is it now? Oh, wow. So it's already time. I'm going to avoid going over time. And I definitely need next class to get to the construction of groups. But I will tell you where this section is going. So in this section, we're going to start by, our goal is to define addition. Now addition is going to be written like this. It's going to be plus, and then this is going to be addition for nats. And as an example, we can say S of Z with S of Z. Now I'm going to introduce this symbol, maps to symbol for evaluates to. So this should evaluate to, well, what should it evaluate to? If plus is defined sensibly.
Three?
As an nats.
S of S of S of Z?
Good. So we want to define addition on nats where we can form expressions. So we want to form like, so plus, let's say n and m, where these are metavariables for nats. And I want to say for all such expressions, what are their values? So how do I evaluate expressions? So that's our goal. Define addition. And addition would mean for every single choice of n and m, I need to describe to you what the value of this expression is. And in the course of going there, we're going to introduce the notion of computation. So instead of defining just what the value is, we're going to define partial ways to reduce something that are sort of half useless answers. They don't get you to the answer, but the way that you're going is directed towards eventually getting to the answer. And by going through this, suddenly we'll think about computation. We'll think about steps. There's going to be a process that's going on. It's not just going to be input and output. It's going to be input, do things, get to the outputs. And when we have that picture, when we have this definition of plus and what it means to evaluate an expression like this, we're going to understand it, and we're going to ask, well, how do I prove theorems about it? And then next class gets to the place where we're going to be able to prove that plus zn is equal to n. If I replaced n and z here, then it would be automatic in our definition that held. And after I prove something like this, you're going to have two homework problems. I guess they're going to be due on Saturday and Sunday now. And the first one is going to prove commutativity of addition. Now, it's going to be tricky for you because you're going to have to reread how I explained how to do proofs. And I am going to explain how to do proofs in detail. The proof itself isn't long, but you need to understand everything that's going on in order to be able to write it. So that's going to be a challenge. But you don't have the context right now for understanding it. You're going to need what I'm going to tell you next class. But that's where we're going. And then at the end of the week, we'll already have the notion of proof introduced and the basics of computation. The next week, we're going to start studying formal systems and really get into racket. Okay, any questions? Oh, I also opened, of course, Piazza. So general questions. You can't post homework spoilers yet because I haven't told you what the homework problems are, but you shouldn't post homework problems on Piazza. Now you can ask me to schedule time to help you. You can do that by email. But if you have any specific question about something, it's good to ask it publicly so that everyone can see, because other people probably have your question. So hopefully you can register in Piazza. And then I'll send you information about submitting homework later, although you still don't have enough information to start the homework. Okay, so that should be all for today. See you tomorrow, right? Tomorrow.
All right, bye.
Bye. Have a nice day.